and welcome to Tinkering with Edkelar. As I hinted in one of my last videos, I got my paws on another piece of test equipment. It is an HP 334A distortion analyzer. Rack mount form factor, analog meter movement, frequency range up to 600 kHz. That is not very high, but the device was made from the mid-1960s to at least the mid-1970s, and it was a very popular model. There is an almost identical one, the 333A, that lacks the RF detector input. What is that, you ask? Beats me. It seems to allow direct readouts from AM modulated signals. I wasn't looking for that specific detail, but since it comes with it, I will eventually try it out. As usual, it was in mediocre shape when it arrived. Not too banged up, but overall dusty, full of sticker residue, and a switch handle was missing. Let's start with the disassembly. Oh, this might take a while. The banana jacks are soldered in and most of the case parts are riveted together. And to top it off, the mount for the frequency dial wouldn't budge. First, the two set screws were seized up and then the little disc that holds the dial wouldn't move on the axle. The front panel won't come off as long as this is on. I had to get nasty with it, so I could at least get a disc puller underneath. That did the trick. Seems that the set screws have marred the shaft and that bound up the disc. Off to a good start. Especially since the camera batteries died during the ordeal, so the only thing I have to show for it is a scratched front panel. After finally getting under the front panel, it was time for some cleaning. The meter seems to work fine. No rust inside. Only the glass is pretty dusty on the inside, so I just had to open it and give it a good clean. The calibration seal taunted me. After cutting it neatly in two halves, one of them just fell off. It also took some time to find out how the glass was held in place. HP used plastic clips to go between the two shells, held in place by the threaded inserts in the upper half. So to get them out, I pulled out the inserts with the screws. While chatting about the device in an electronics group, I found out that one of my contacts has the 333A model and could provide me with a picture and measurements of the missing switch cover. Sweet! OpenSCAD and 3D printing to the rescue again! Since the case is mostly riveted, I decided to leave that stuff together this time. Cleaning the switches, potentiometers and the case overall was possible with the switches still in place. Note that the rotary switches have components arranged with minimal lead length. This tells me that there is some AC magic happening here, and I'd rather not mess up some carefully crafted signal paths if I don't have to. One thing I had to drill out. The two sliding switches are almost impossible to move. They needed some inside-out cleaning, but one of them was held in place on the chassis with two rivets. Off with their heads! Now, after the in-depth cleaning, I could finally start the assembly. The banana plaques that came with it were nice, but the plastic was breaking on just about all of them. One was so bad that the cap even fell off. I found replacements that were very close in shape and color, but they lacked a hole in the bottom for clamping wires. Well, I have a mill now. A few missing holes are no problem. It's taking shape again. The frequency dial mechanic had ancient grease on it and was not moving properly. Again, some cleaning later and a few dabs of fresh grease, it moves like new. Notice that the gears are backlash free, so the larger gear is actually made of two gears that are held in place against each other with a spring. That way, there is never any play between the sprocket and the gears in either direction. The adjustable capacitor for the frequency adjustment is a sight to behold. 4 ganged movements across the entire depth and height of the device. I replaced the rivets for the switch with 2 screws. Should be perfectly okay. The original factory drawing does list nuts and bolts. During assembly, I finally realized why some of the stuff was mounted in such a weird way. I should have read the manual earlier. The case is earthed, but the chassis on the inside is ground. That means the device has, technically, 2 ground potentials. This is why there are 3 input checks: signal, ground and earth. I made sure to keep it like that and kept buzzing out the 2 grounds between steps, even though they will most likely be connected by the bar that is provided between the plugs. And this is also where I finally realized that the RF input on the backside is not a coax PNC. It is a triax socket to keep the grounds separate. That's officially my very first device with such a connector. Now to the components. I checked a few of the electrolytics and found them to be way out of their spec. The instrument calls for plus 75%, minus 10%, so technically they should have been fine. But when a 10% capacitor measures 50% out, I don't want to keep them in a device like that. The only sad thing is that axial caps are harder and harder to come by. I had to bend and sometimes extend radial ones instead. But at least they are all of them smaller than the original, so no space problems. A rather interesting part of the device is this black box. Behold, magic pixies inside, and they sparkle. Well, joking aside, this is a set of LDRs, or light-dependent resistors, combined with light bulbs. So the more light the bulb provides, the less resistance the LDRs have. You can think of it as an analog optocoupler. This feedback is used to auto-set the frequency and home in on the best possible measurement. Problem number 1. The foam was deteriorating. I had to replace that. But even worse was problem number 2. One of the light bulbs was burned out. I had to order close enough replacements. At least the LDRs seem to work, because those are unobtainium by now. After recapping the power supply, I checked that out first. Works well within tolerance, even without adjustments, but I'm tweaking it a bit to get closer to nominal. This device can measure AC levels that are 2 orders of magnitude below my next best meter. The lowest range is 300 microvolts full deflection. 0.0003 volts for full, that means 0.0001 volts is still easy to measure. And after adding all the other boards and making sure that all the wires go to the right pins again, I power it on. And go through all the parts of the calibration guide that I can reasonably simulate. After some turning of knobs, I can say with reasonable certainty, it works! In voltmeter mode, it reads RMS voltage like any other voltmeter. It just has an incredible range from essentially 0.000005 volts for the first tick on the scale to 300 volts for the highest. That spans 8 orders of magnitude, from don't touch it or you'll throw off the measurement by acting as an antenna, to don't touch or the measurement will throw you off the chair. Anyhow, here's the main course: distortion. And here's a quick rundown on how to measure it. Step 1. Turn all the knobs to maximum values, for the sake of the needle, and then turn the mode to set level. Step 2. Connect the signal. Step 3. Adjust the sensitivity so that the meter reads at maximum, i.e. full scale. Step 4. Switch over to distortion and tune in the frequency, using the frequency knob and the balance controls. Repeat until the minimum deflection is achieved, turning up the sensitivity when needed. Step 5. Optionally, you can now switch on the auto mode to do the last bit of tuning for you. Step 6. Read the distortion from the scale. Simple enough. So that's it for this episode. I hope you enjoyed my careful first steps into more advanced AC technology as much as I did. Tune in again in a few weeks when I have a companion device for this one on my bench. See you next time! Tune in next week. Not next week. No, not next week. I can't finish it next week. Darn it!